For the floor-level panels that are mounted to the studded embed plates, there are 9-inch flanges on either side at the bottom, with 2 rows of 3-inch holes for the anchor rods, for a total of 140 bolts for each section. I believe these are likely welded to the embed plates after installing the hefty anchor nuts. You can see that on the back side of the panels, which would be the side facing the sheet pile walls, there are shear studs welded to the surface of the plates, which was an early indication that the area between the speed core and sheet pile walls would later be backfilled with concrete. The side closest to the integration tower has a very large gap between the speed core and sheet pile walls to create space for installing the large water pipes for the deluge system. With multiple overlapping operations taking place, one of the focuses when constructing the wall was to quickly reach a point where the flame bucket and launch mount could be installed. For this reason, the section of the wall that is responsible for supporting the launch mount and transferring loads into the foundation were installed first. Before it could be filled with concrete, each of the wall sections were first welded together. Unlike the crew who did the base of the integration tower with their fancy welding robots, all of these welds were performed by hand. In my opinion, you could almost consider this a mega project on its own, considering that each seam might require up to 20 or 30 passes. Of course, there are many factors that affect that number, but the point is, it's a lot. To put that into perspective, if this was a single continuous weld, it would probably stretch for 10 to 15 miles, which is basically the distance between Starbase and Brownsville. Keep in mind, this is just for the 2 load-bearing wall sections. If you consider the rest of the trench, including the floor panels and the support structure for the flame bucket, it's probably well over 150 miles. For the tower side of the trench, the huge gap between the trench and the sheet piling wall allowed them to set up scaffolding on both sides of the wall to perform these welds. But on the other wall, which was intended to butt up against the GSC bunker, there wasn't enough space to access the back side of the wall, which forced them to do it from the inside. Looking at it from above, you can see scaffolding boards laying across the 10-inch pipes, allowing them to traverse the full length of the wall at multiple levels where these welds needed to be performed. This might seem like a super confined space, but if you remember the fact that these walls are nearly 4.5 feet wide, there is plenty of room for activities. Based on the number of generators lying around, we can estimate that there were shifts of up to 14 welders in here working 24/7 over a period of 2 to 3 weeks just for the load-bearing wall sections. While this was ongoing, another crew began installing the support structure for the flame deflector. This takes us to that last set of embeds in the middle of the trench floor. Similar to the embeds for the main trench walls, these plates also have large 3-inch threaded studs attached to the surface. These are arranged in 5 equally spaced pairs across the center line of the trench. At the end of March 2025, 5 gigantic speed core support walls began arriving to the launch complex. For obvious reasons, I'm going to refer to these double-sided walls as A-frames. As you can probably guess, these A-frames are used to support the flame buckets and the ridge support beam, which we will see shortly. At the bottom of each frame is an access way to allow workers to move between the support walls. The 25-inch spacing between the walls still allowed workers to enter through the side and access the 64 internal anchor bolts. Once secured to the ground, they most likely welded plates over these openings to allow it to be filled with concrete. Same as with the trench walls, it's difficult to say this with certainty, but I believe these are also welded to the embed plates on the floor, although it's possible they are just relying on the bolts. Similar to the support walls at Massey's, there are 2 levels of access platforms mounted between the walls to allow crews to access the areas where they needed to weld the flame bucket cradles to the support walls. Before installing the final component of the support structure, they needed to add the 2 remaining load-bearing wall sections on the tower side of the trench. The first of these unique sections includes 2 48-inch penetrations for the dual flame bucket water manifolds. It's a bit difficult to see in this image, but each hole has a box around it to allow the speed core walls to be filled with concrete before the pipes are installed. The same is true for the next section, which has a single penetration for the ridge cap supply. To fill the gap between the containment boxes in the section below, there is a hole through the top and bottom of the containment boxes to allow the concrete pumper hose to pass through. With these in place, they can finally add the long ridge cap support wall. This speed core wall section has 2 rails extending out diagonally on either side to support the top of the flame bucket and a tapered beam on top of the wall to support the ridge cap. Looking at it from the side, you can see the shaved surfaces where it would later be welded to the 5 A-frame supports. After carefully sliding it down between the 2 trench walls and resting it on top of the cutouts on the A-frame supports, it was also welded to the load-bearing wall on either side. After the thousands of man-hours it took to reach this point, they were finally ready to install the flame buckets. Now, before we dive into the design of the flame bucket, I think it's worth establishing a point of comparison. When it comes to launch pads that have to operate under similar conditions, there are really only two that are even remotely in the same class. That, of course, is the SLS launch pad at LC-39B, and to some degree, the New Glenn launch pad at SLC-36. While neither vehicle is anywhere near as powerful as Starship, both pads were theoretically designed to handle future iterations of the vehicle that would have significantly greater thrust output. For now, we're just going to focus on LC-39B. To really understand what went into the design for the flame diverter built for SLS, it helps to understand what came before it. A majority of space shuttle launches actually occurred at LC-39A, but the flame diverters were basically identical. The original flame diverter used in the space shuttle era was a double-sided ramp designed to split the exhaust from the SRBs and main shuttle engines into two separate flame ducts. This was not a symmetrical design. Instead, on each side of the deflector, the angle of the ramp was optimized so the exhaust plumes would impinge on the surface at specific controlled angles. On the SSME side of the diverter, the trench features a sloped ramp leading upward out of the duct. On the SRB side, however, both the floor and the exit of the trench are completely flat. The deflector itself is made of steel, but its surface was protected by a layer of durable material known as fondue fire. This material is sprayed onto the deflector and portions of the trench wall and was designed to enhance resistance to erosion, thermal shock, and abrasion. Now, let's take a look at the actual water deluge system. The main water supply for the deluge system is broken into two pathways. Starting with the lower of the two pipes, this is the pre-ignition supply, which is arguably the most important part of the deluge system and is made up of several different components which are all activated roughly 8 seconds prior to ignition of the shuttle's main engines. On the apex of the diverter, a row of bidirectional water nozzles were the main component of the deluge system and were capable of discharging water at a rate of 300,000 gallons per minute. While both sides of the deflector performed the same basic function, there was a huge difference in the thermal environments experienced on each side during launch. So the deluge system was designed with this in mind. On the SSME side, the deflector experiences roughly 6 seconds of relatively controlled, lower intensity exhaust from the 3 shuttle engines before SRB ignition. This delay allows systems to verify the health of the SSMEs and then build up to full thrust. Beneath the main engines was a rectangular pattern of 60 nozzles, creating a curtain of water across the opening to the flame duct. This is the only location where water was actually being injected directly into the plume from all sides. Even though the exhaust basically ends up punching straight through it, with help from the bidirectional nozzles on the diverter, it seems to do a good job of protecting the surface of the deflector. If not for the fact that the deflector is essentially still in a warm-up period during this 6-second delay, it might not have been as effective. Luckily, this was not enough time for the deflector to reach a steady-state temperature where the plume would likely begin to rapidly erode the surface. I should note that while I wasn't able to find any records to help verify this, it does appear that a large rectangular section of the fondue fire had to be removed and replaced on at least one occasion. Anyway, on the opposite side of the deflector, the situation is very different. After 6 seconds of cool water flow, all of a sudden 83% of the exhaust mass flow is now directed towards this side of the flame duct. This makes the 50-50 split from the apex nozzles a bit insufficient on its own, particularly when it comes to ignition overpressure and acoustic energy suppression. To compensate, additional water nozzles are installed along the sides of the trench, which spray downwards towards the aluminum particle-laden SRB exhaust plume. As you can see, these were some pretty large pipes supplying those nozzles. Most of this water is actually redirected up towards the mobile launcher. Given that this is part of the pre-ignition supply, I believe these risers are supplying water to the rectangular manifold beneath the SSMEs. It may also be used to supply a pair of nozzles located just beneath the SRBs, which would spray water directly into the plume from the opposite side of the main flame deflector nozzles. It's extremely difficult to find footage of these nozzles during operation, but you can see it pretty well in this IMAX footage from STS-125 when NASA launched the Hubble telescope. Given the intended purpose of this component of the system, it's actually a bit interesting that these nozzles are not injecting water from all 4 corners of the opening. That may have something to do with the fact that these nozzles were not part of the original design, but were part of the return-to-flight modifications made to the mobile launcher after STS-1. During the inaugural shuttle mission, the intense overpressure from the SRBs reflected back onto the vehicle and damaged some of the thermal protection tiles on the orbiter. As you can probably imagine, it was extremely critical to prevent that from happening. As a final layer of protection, there were red nylon bags stretched across the opening adjacent to the SRBs. These water-filled bags were designed to rupture after the ignition of the SRBs. Their main purpose was to help dampen the reflected acoustic waves from the initial overpressure. Together, these systems were extremely effective at mitigating the ignition overpressure from the SRBs. You can see that the system as a whole does a good job at suppressing the reflected shock waves, which are just barely visible as they interact with the plume in this footage. Now, even though the SRBs were acting on the deflector for a much shorter duration, the heat flux into the surface was vastly more intense. This resulted in peak thermal loads that were orders of magnitude greater than the SSME side of the deflector. On top of that, the exhaust was loaded with hydrochloric acid and molten aluminum oxide particles, which acted like an abrasive sandblaster, which helped to accelerate erosion. Overall, there was a lot more wear and tear on this side of the deflector. Most famously, during the STS-125 mission in 2009, 25 square feet of fondue fire material broke off of the north side of the deflector. As far as I can tell, NASA wasn't necessarily trying to prevent this from happening. It was designed to be repairable in a short enough time after a failure that it wouldn't cause major delays. Now that we have all of the pre-ignition systems out of the way, let's look at the post-ignition water supply, which is exclusively for the Rainbirds on top of the launch deck. The activation of this system occurred roughly 15 seconds after the pre-ignition system, and was more or less synchronized with the SRB ignition to prevent the water from being sprayed onto the SRB nozzles. Instead of covering the entire deck, the Rainbirds are focused on one side of the platform. This is because shortly after liftoff, the gimbaled SSME engines push the entire vehicle in this direction. This causes the SRB plume to sweep across the deck at damn near point-blank range. This water helped to prevent the damaging sound waves from reflecting off of the flat surface directly back onto the vehicle. With that said, the main purpose of this water deluge system was ignition overpressure and sound suppression, and cooling the launch infrastructure was more of a secondary benefit. This would become more important after the space shuttle was retired and NASA moved on to the SLS program. In 2013, the entire water deluge system was stripped out of the flame trench in preparation for upgrading the launch pad to be compatible with SLS. Now, I'm going to try to stay neutral here, but I feel like that word compatible is carrying a door frame destroying amount of weight. Unlike the space shuttle, the upgraded SSMEs on SLS are effectively mounted in line with the SRBs. Not perfectly, but close enough that the double-sided flame diverter was no longer required. With all 6 engines firing towards the same side of the deflector, the thermal environment has changed completely. On top of that, the SSMEs were expected to operate at higher power levels, and their nozzles sit more than 6 meters closer to the flame deflector than they did during the shuttle era. As NASA was redesigning the pad, a study conducted by the American Institute of Aeronautics and Astronautics sought to model the physics of injecting water into supersonic exhaust plumes. The goal was to predict how the water suppression system would affect the main flame deflector, and, ironically, to ensure that it wasn't being over-designed. While the study includes a lot of interesting details that we don't have time to cover here, one result is particularly relevant. The CFD model simulated SLS over a symmetric version of the shuttle's double-sided flame deflector, with bidirectional nozzles injecting 300,000 gallons of water per minute in either direction. Under that configuration, the study concluded that while the deluge system was very effective for acoustic suppression, it performed poorly at managing the severe thermal loads experienced by the flame deflector. The primary reason was that the injected water was rapidly vaporized inside the SRB plume, long before it could reach the surface of the deflector. This is clearly visible in the CFD results, which show that the regions where the liquid water exists are located far away from the deflector surface. To make matters worse, portions of the high-pressure water jets were being pushed back to the other side of the deflector by the SRB exhaust. This effect was less severe under the SSMEs, where a small fraction of the water was able to reach the surface and contribute to cooling. The study ultimately concluded that effective cooling would require water nozzles to be installed along the slope of the diverter itself, rather than injecting water directly into the side of the plume. This multi-phase simulation was intended to inform the design of the new universal flame deflector. However, when NASA began construction of the new deflector in 2017, these findings appear to have been largely ignored. Much like the Apollo and Space Shuttle era designs, the curved support structure was built around a large internal water manifold supplied by 2 risers feeding a Rainbird-style manifold at the apex of the deflector. Mounted to this structure is a pattern of overlapping 3-inch thick steel deflector panels. These panels are not part of the deluge system itself, but simply provide a surface for the exhaust to impinge on before being redirected out of the trench. Each panel is bolted to the supporting framework, which are then covered by rectangular tabs extending out from the row above, making them relatively easy to remove and replace. That design choice strongly suggests that this system was once again optimized for refurbishment instead of long-term reusability. And because this is now a single-sided deflector, the bidirectional nozzles were no longer required, meaning, in theory, twice as much water could be delivered to the active side of the trench. In reality, it might be even more than that considering they upgraded their water tower to hold an additional 150,000 gallons, but I'm not exactly sure where all that extra water is being directed to. With that said, since they now had double the amount of water being supplied to the active side of the flame duct, it appears that they decided that they no longer needed the nozzles along the side of the trench spraying down into the plume. This ended up simplifying the water delivery system a bit, and the dual risers that were previously attached to the rail-mounted side deflectors were replaced by a single riser for the pre-ignition system on the mobile launcher. On either side of this are two risers for the post-ignition Rainbird system. Not only did this simplify the process of aligning components after placing the structure on top of the pedestals, but it also made a bit more water available for the horizontal nozzles beneath the engines. Even with more water being supplied to the launch deck, they still had to make some important trade-offs. Because of the new engine configuration, there was no longer enough room to have a rectangular manifold with 60 nozzles spraying water into all four sides of the SSME plume. Mounting a manifold in the space between the SRBs and SSMEs was simply not an option. As a result, the amount of water being injected into the SSME plume was cut in half, and there are now only 8 nozzles on either side for a total of 16. Considering there are now 4 SSMEs instead of 3, this is less than ideal, because you're technically only injecting water into a quarter of each of the individual plumes. However, I'd argue it was definitely a worthy sacrifice because it allowed them to more than triple the amount of water beneath the SRBs. Instead of having nozzles in 2 corners like they did in the shuttle era, there are now 6 nozzles surrounding the SRB plumes. One thing you may have also noticed is that the Rainbirds are now activated more than 10 seconds earlier, which means there is technically no longer a post-ignition system. If I had to guess, most of that additional 150,000 gallon water capacity is probably going to the SRBs, while the rest is being directed towards the early activation of the Rainbirds. It seems they are now less worried about spraying water onto the engines and a lot more concerned with protecting the mobile launch structure. With all of this in mind, I'm sure that everyone involved expected this system to do an even better job dampening the ignition overpressure from the SRBs. But holy shit, were they in for a surprise. Turns out it was barely an inconvenience for the Violent SRBs, which ended up producing a far larger overpressure wave than what was observed during STS-1, and caused major damage to the pad infrastructure. Now, I'm going to do my best to stay neutral here, but the fact that this system was designed the way it was is interesting to say the least. Especially considering that NASA clearly applied the lessons from earlier studies when they upgraded the test infrastructure at Stennis Space Center for RS-25 and SLS core testing a few years later. The Fred Haise test stand, formerly A1, for single-engine RS-25 tests, along with the B1 and B2 test stands used for SLS core stage firings, received targeted upgrades to support prolonged, high-power hot fires more reliably. Similar in concept to SpaceX's booster bidet system, these massive flame buckets function as giant water manifolds with thousands of precisely drilled holes across the deflector surface. Systems like this prioritize thermal load management over acoustic suppression, concentrating water flow on the critical impingement zones where the exhaust plume is most intense. Maintaining a continuous protective water film over the deflector surface is essential for achieving steady-state thermal equilibrium and keeping temperatures well below material limits. This approach allowed NASA to safely conduct extended duration tests with a nominal burn time of 480 seconds and the longest test lasting an impressive 720 seconds. Given that background, it's unclear why a similar approach was not used at Launch Complex 39B. One possible explanation is that, unlike the long-duration tests at Stennis, the MFD at 39B is only exposed to extreme thermal conditions for roughly 15 seconds, essentially just long enough for the vehicle to clear the pad after ignition. The assumption may have been that this short exposure wouldn't allow sufficient time for the heat flux to fully penetrate the thick steel plates and drive surface temperatures high enough for phase transition to occur. In this case, that phase transition is not from a solid to a liquid, but from a solid straight into a gas. Unsurprisingly, the SRBs are incredibly efficient at vaporizing steel. After Artemis 1, The surface erosion was severe enough that the deflector panels had to be completely replaced. Much of the worst damage was traced to the 1-inch expansion gaps between panels, which were larger than necessary. These gaps were expected to close as the plates expanded under thermal loading, but instead allowed hot gases to flow between the panels and carved channels into the downstream plates. Ahead of Artemis II, the panels were redesigned with a reduced half-inch gap, with the expectation that this specific failure mode will not reoccur. Even so, there is no way to eliminate the remaining surface erosion that was not attributed to this particular design flaw, especially in the regions directly under the solid rocket boosters. At least, not without a fundamental redesign of the system, which NASA does not appear eager to pursue. That's actually not all that surprising, considering it would probably come with a disgustingly large price tag. At the end of the day, the primary reason this design choice does not pose major operational problems for NASA is that SLS launch cadence is measured in months or years, not the days or hours that SpaceX is aiming for. That incredibly long turnaround time allows the flame deflector panels to essentially be treated as a consumable. This is why the argument that SpaceX should have simply copied what NASA has done over the past 6 decades fundamentally misses the point. If Starship were placed over the flame trench at 39B, I think there's a strong possibility it would cause significant damage, if not outright destruction, of the deflector system. If it did survive, it would never achieve anything close to the reuse rate that SpaceX managed with its first-generation Deluge system. That's really the core point of this 16-minute side quest we just took. Designing for continuous, rapid reusability is a completely different ballgame than designing for ignition overpressure and sound suppression. And given that this is the only Super Heavy class rocket currently in existence, SpaceX is operating in genuinely uncharted territory. With that context established, now that we understand the task they are trying to accomplish on a fundamental level, let's take a look at how SpaceX designed and constructed the Super Heavy rated deflector buckets. Unlike the flame deflector for the ship hot fire stand, which was pre-assembled in 3 sections at the McGregor facility before delivery, these were assembled entirely on site. Fortunately, this allowed us to notice important details that we would not have been able to otherwise. Forming the backbone of each flame deflector is a large cradle, which is essentially the main structural support for the pipe assembly. On top of each cradle support is a sheet of rubber-like material which appears to be several inches thick. You can see there are several guide tabs along the length of the beam to hold it in place. This padding is intended to protect the flame bucket by preventing it from vibrating against the steel frame. This is an interesting detail that indicates that the pipes are not permanently attached to the frame, but we will come back to that shortly. Mounted on one side of the cradle, which actually represents the top of the flame deflector, are large 36-inch water manifolds, each with an alternating pattern of 66 holes. There are 50 holes in the main pipe and 8 holes on each of the smaller diameter extensions for the edges of the ramp. Unsurprisingly, this is the same number of 8-inch pipes used to create the flame bucket for the static fire test stand. The pipe sections that are used to form the ramp are actually 2 smaller pipes joined together, one making up the curved section of the bucket and a straight section of pipe with a T-fitting just over halfway down its length. This T is what connects the pipe to the large water manifold. Before placing the pipes onto the cradle, a rectangular support frame was assembled and perfectly centered between the 2 bucket sections to allow the pipes for the bottom of the ramp to rest against it. Over a period of 4 weeks, all 132 pipes were mounted one by one, welding them to the manifold outlet. These would continue to rest up against the supporting frame until they were properly aligned and welded together. As you can see, all but 2 outer pipes in the middle section were installed. This keeps the cradle supports accessible for attaching lifting slings when it was eventually lowered into the trench. To make sure the pipes were properly spaced out, they wedged a short section of 8-inch pipe in the gaps between the middle and outer sections. Before the pipes could be welded to their neighbors, they needed to make sure that they were all perfectly in line with each other on either end of the ramp. For this, they made a special jig using a pair of long I-beams slotted between 2 rectangular frames. After sliding the jig over the end of the pipes, a pair of hydraulic jacks are used to squeeze the 2 I-beams together and force all the pipes into proper alignment with each other. Once this was complete, they were able to join the pipes with their neighbors by welding them along the entire length to lock in that alignment. One of the final steps was to drill all of the holes for the water jets, which took several weeks to complete. Thanks to the fact that these were constructed at the Sanchez site, Starbase photographers were able to capture some excellent shots as it was rolled out to the launch site in April of 2025. Zooming in, we can see that there are 2 rows of holes on each pipe. Keep in mind that this is the bottom of the ramp we are looking at here. We were never able to see the hole spacing on the sloped part of the bucket, but what we can see is that it has a similar color-coded pattern of markers on the pipes like we saw with the bucket at Massey's. As you can see, everything between the red arrows likely gets the smallest hole spacing, followed by slightly larger spacing in the yellow, green, and finally blue zones. So the hole spacing that we saw at the bottom of the ramp is likely representative of a blue zone. Because Super Heavy has 5.5 times more engines tightly packed into the same 9-meter diameter, there isn't as intricate of a pattern here. It's basically red everywhere within the 9-meter footprint of the booster. Anyway, there was one more interesting detail that we noticed as this was being rolled out. If you remember the rubber padding for vibration isolation that I mentioned a few minutes ago, well, you can see that pretty clearly in this image taken by Sean Giesler from the Marcus House channel. The thickness of the cushion prevents the bucket structure from being welded to the frame. Not only is there too much separation, but it wouldn't work as a shock absorber if the two structures were permanently fixed together. So to attach the bucket to the cradle, there are clevis brackets welded to the back side of the bucket. There are additional double clevis brackets welded to the I-beams on the cradle. You can see the brackets have slotted holes to allow the rubber pads to be compressed by several inches. Along with dampening vibrations, another major benefit of this is that it allows the entire bucket to be removed from the cradle in the event it becomes damaged and needs to be replaced. In retrospect, this is probably a capability that should have also been built into the Starship flame deflector. But after looking back just to make sure I didn't miss this specific detail, I was unable to find any evidence of clevis brackets being mounted to the cradle. Anyway, while the cradle serves as the primary structural support, the bottom of the ramp still needs its own load path. If we look back at the single clevis brackets on the back side of the flame bucket, we can see that once the structure is rotated into the proper orientation, those brackets are now facing downward towards the floor. This implies that the other half of the clevis assembly must be mounted somewhere on the trench floor, similar to what we see on the cradle. One detail you may have noticed is that the flame bucket actually sits within the footprint of a roughly 8-inch deep basin at the floor of the trench. This basin acts as a low point for water collection, which again is something they didn't have in the Massey's flame trench. If we peel back the layers of time, we can see a long embed plate visible at the foot of the step. This is somewhat easy to miss until you have a reason to look for it. This embed plate is the surface that the lower clevis brackets are mounted to. What we don't know, however, is whether or not these brackets are truly fixed or if they use elongated mounting slots like those on the cradle. If the bracket is fixed, then the bottom of the flame deflector may be partially suspended above the floor. But if it's a slotted bracket, then it would make sense for the pipes to rest on some sort of shock-absorbing support built into the trench floor. With that said, we are assuming that there are padded beams installed across the floor to support the bottom of the ramp. Not only would this allow the bottom of the structure to compress uniformly with the curved section, but it also helps to prevent buckling under extreme transient loads. Unfortunately, in this image taken the day before the deflectors were installed, there are no such beams visible on the floor, nor any obvious embeds for them to mount to. That said, embeds aren't the only way to anchor hardware to the floor, so this remains a plausible but unconfirmed feature. While we're in speculative territory, it's also worth including the diagonal I-beam on the ridge cap support wall, which would clearly not exist unless it was necessary for supporting the upper portion of the deflector. There are no metal tabs sticking up on the edges of the beam that would indicate a future shock-absorbing pad, but allowing the pipes to vibrate freely against a rigid beam seems unlikely without some form of cushioning. For now, we'll assume that some type of soft interface exists both at the top and bottom of the deflector, even if the exact implementation remains hidden. With both flame deflectors situated in their final resting positions, the cradle supports were welded to the A-frame walls at every location where they contact each other. And this is where those access platforms come back into play, because with the flame bucket installed, the only way to access these areas is from below. If not for the sheer size of this structure, I would imagine that they wouldn't have been able to get away with lifting the cradle and the deflector into the trench as a single assembly. Reaching these corner welds are easy enough, but accessing the ones on the upward-facing side of the A-frames probably required welders to put themselves into some pretty awkward positions for a long period of time. Unfortunately, my green screen work isn't advanced enough for me to try and sit on top of these beams, or else I would show you what I mean. If I had to guess, there were probably at least 5 welders repeating this process on the first, second, and third levels for at least 1 to 2 weeks. The third level is particularly difficult to access because it requires climbing down from above and sliding through the gap between the diagonal support beam and the ridge cap support wall. While they did have ladders staged on the access platforms ahead of time, I imagine that if your shirt size contained more than 1X, you were probably sitting this one out. While all of this was happening, another team began putting the final touches on the flame bucket. The first task on this list was related to another feature we noticed as the bucket was lowered into position. Similar to the flame bucket at Massey's, which had temporary caps installed over the cleanout holes at the ends of the pipes at the bottom of this flame bucket have open bung holes that were left uncapped. What? That's what they're called. Look it up if you don't believe me. Unfortunately, from the limited views we have of them, we can't tell whether or not they're threaded. Either way, the fact that they are left open suggests that these are not cleanout holes, but large nozzles spraying a sheet of water across the floor of the trench. This addresses something that I became concerned about after reading the Artemis I flame deflector ablation analysis. In that report, they discussed how the most severe damage to the deflector was a result of the hot gases flowing through the 1-inch gap between panels and carving a deep channel into the lower downstream plate. I think this same issue could occur on the floor of the trench as the exhaust flows down the valley between each of the pipes. I should note that this is a slightly different situation. Since there is water being ejected along the pipe, the exhaust flowing through these channels should have a lot less thermal energy. But over time, this could act as a V-shaped cutting torch, carving large channels into the floor. By spraying a sheet of water between the floor and the plume, it should dramatically reduce, if not eliminate, long-term damage to the floor. Now, in order for crews to reach underneath the end of the flame bucket to install the clevis pins on the mounting brackets, they needed to leave a human-sized gap between the ends of the pipes and the foot of the step. Once this hardware was installed, they added open-ended extension pieces onto the ends of each of the pipes to close the gap. Using the human for scale, you can see how little space is remaining after these extensions are welded in place. This also acts as a nozzle extension that should help to flatten out what would otherwise be a wedge-shaped spray pattern coming out of the nozzles. This reduces the water spraying up into the plume and increases the amount of water contributing to cooling the floor. As these extensions were being added, they installed the 4 missing pipe sections that were left out to allow the lifting straps to be attached to the cradle. I'm not sure whether or not this was intentional, but after they were lowered into position, you can see that there was a larger than expected gap between the pipes. To fix this, they added filler plates on either side to close the gap and allow them to join the pipes together. Last but not least, before we're moving on to the next step, everything that was completed up to this point was filled with concrete. This includes the load-bearing section of the trench wall, the A-frame supports, and the ridge cap support wall. Filling the A-frame supports would have required them to snake the pumper hose down through this gap to reach the opening in the top of the wall. For the ridge support wall, they added fill ports on either end, which were likely removed after the wall was filled. As the first stage of concrete infill was being completed, they also began installing the non-load-bearing wall sections along the sloped exits of the trench. By the following week, it was time to install the next major component of the deluge system, the wedge-shaped splitter for the apex of the dual flame deflector. This water distribution manifold is what we've been referring to as the ridge cap, and is perhaps the most important component of the system. At the very least, it certainly has the most difficult job. If we look at the flame bucket assembly from above, you can see that there is a roughly 6-foot gap between the tops of the 2 ramps. When we overlay the booster engine diagram, we can see that several of the booster's engines are going to be firing directly onto or very close to the center line of the trench. This means that you can't get away with using a simple bidirectional nozzle system. The time it would take for the Raptor plume to convert the entire nozzle from a solid into a gas would be measured in seconds. This forced Stage 0 engineers to get a bit more creative when designing the centerpiece of this system. The first component of this assembly is a flat plate that has a 45-degree bend along the edges. This surface curves over the top of the pipes on either side of the flame bucket to tuck up under the 2 shoulders. On top of these 2 plates are 22 vertical supports with a large hole passing through the center. While these are mostly for structural support, the vertical plates may also act as baffles to have some kind of effect on the water as it flows from one side to the other. If I had to guess, it probably reduces the momentum of the water before it slams into the wall at the end of the manifold. On top of this is a perforated V-shaped plate that creates a fully enclosed structure. There are 2 of these manifold sections joined together to complete the ridge cap assembly. On one side is a 36-inch pipe flange, which is likely capped off while the water inlet is on the opposite side. Finally, on the bottom of the manifold are 84 evenly spaced tabs, which straddle the tapered beam on the top of the ridge support wall. I can only imagine how difficult it was to access this area in order to weld all of these tabs to either side of the tapered beam. Now, even with water coming out of the entire exposed surface of the ridge cap, it's still best to avoid firing engines directly onto the apex. Instead, you want as many engines as possible firing to either side of the apex instead of splitting it. This made the original engine configuration on the version 2 booster less than ideal. as there would be 4 engines that are at least partially splitting the apex. To help with this situation, the positioning of the 13 gimbaling engines was completely reconfigured on the version 3 booster. By rotating the inner ring of 10 by 18 degrees and adjusting the orientation of the 3 center engines, they were able to completely eliminate any direct impingement on the apex of the ridge cap. Depending on where they were in the development process for the V3 boosters when this decision was made to incorporate a flame trench, I imagine that could have been a major headache for the booster tribe. Now, perhaps the only downside with this new arrangement is that instead of 9 individual exhaust plumes acting on the ridge cap, there are now 11. Not only is this a considerable increase in force acting on the structure, but it also comes with a 22% increase in thermal load into this component. With 11 out of 33 engines, or 1/3 of the combined exhaust plume acting directly on the ridge cap, you almost need as much water flowing out of this surface as you do coming out of either side of the flame bucket. So, as you can probably imagine, there are a lot of holes in this thing. While the hot exhaust gases from the outer engines have some freedom to expand outwards, the exhaust from the center engines are more confined or trapped from expanding outwards by their neighbors. This makes the density of hole spacing extremely important because you will need more cooling capacity for those 7 engines than you do for the outer 4. To compensate for this, you can see that near the top of the ridge, within the radius of these 7 engines, the density of holes increases significantly. These holes are drilled at a super shallow angle relative to the outer surface of the ridge, which directs the water out under the bottom edge of the launch deck instead of directly up the booster's voluptuous rear end like a bidet. You know, as the one who pretty much turned that into a household name, I'm starting to wonder if we should stop calling it that. I mean, if it doesn't actually touch the booster, is it really a bidet? Nah, fuck that. It's already dead. We probably shouldn't double tap it by killing its name, too. Sorry, Ryan. At least I considered it, though. Roughly 3 months after the ridge cap was installed, workers began putting the final touches on the dual flame deflector assembly. Looking back at the Starship flame deflector, we see the edges of the deflector curve upwards at roughly 50 degrees before transitioning to a steep 90-degree vertical wall. This upward flare helps guide the exhaust out of the trench and prevents it from spilling over the sides of the bucket. On the Super Heavy deflector, the 4 pipes forming the vertical wall on either side are traded for 8 additional pipes on the flat part of the ramp. This makes the overall deflector more than 6 feet wider. But without that 90-degree sidewall, there's an increased risk for superheated steam to end up circulating around and beneath the deflector assembly. To prevent that backflow and hot gas buildup, sealing the gap between the deflector's edge and trench wall was extremely important. In July of 2025, steel I-beams were added between the wall and the ends of the lateral support beams on the cradle. This effectively extends the cradle to span the full width of the trench. At the bottom of the ramp, diagonal I-beams were added to support the flared sidewalls of the deflector and are joined with the padded beams on the floor, assuming they actually exist. When it's all said and done, you can see what the full cradle would have looked like had it been installed separately from the deflector. Mounted on top of the new support beams are stainless steel panels extending from the bottom of the deflector and stopping just before reaching the top of the pipes. Moving up to the ridge cap manifold, raised shielding that kind of looks like those NFL shoulder pads from the 1980s was attached between the end plate of the manifold enclosure and the wall of the trench on both sides. The raised shoulder allows it to wrap around to cover the tops of the last remaining exposed pipes on the edge of the deflector. Finally, end plates are added between the shoulder and the top of the pipes to completely seal off the remaining air gap. These were added along the bottom of the ridge cap as well, sealing the gap where the ridge curves over the top of the pipes. Once closed in, the only way to access the support structure underneath the flame deflector was to duck through this relatively small gap in the bottom corner. With the flame bucket and ridge cap fully installed, crews got back to work completing the rest of the flame trench walls and preparing to install the launch mount. Looking back on our list of complaints from the R&D launch mount, another problem that we technically haven't addressed yet is the repeated cracked welds on the flame deflector panels at the bottom of the legs. One of the first major tasks performed as soon as the road is opened after a launch was to assemble a search party to find and label all of the cracked welds on the legs. Whether it was the stairs or the side paneling, these cracks appeared randomly all over the place. But they were especially bad on the wedge-shaped diverter panels at the bottom of the legs. Now, when these were first installed, I remember thinking that they made the launch mount look pretty sick. And in reality, they did, just not in the way I initially thought. After each consecutive launch, the process of repairing welds on the deflector panels came increasingly more of a nuisance. And near the end, it started to get kind of ridiculous.
Yuck.
Now, the easiest solution is to just move the legs out of the exhaust plume's path. If we were to examine common design features found at launch pads across the world, placing the main load-bearing structural supports in a position where they're essentially holding open the gates of hell would likely be among the more rare. This is super easy to accomplish with a flame trench because the legs can be integrated into the walls in a location where they will never receive direct contact with the exhaust plume. On April 18th of 2025, the 4 launch mount pedestals were delivered to Starbase. As they arrived, Starship Gazer captured several angles that allowed us to make some important observations. Before we get into the structural details, it's worth appreciating the job these things are built to do. The original launch mount with a fully loaded V2 Starship supported an estimated 8,000 tons distributed across 6 legs. That works out to roughly 1,300 tons per leg. On Pad B, the entire launch mount and a fully loaded version 4 stack are supported on just 4 legs. Conservatively, that's probably somewhere on the order of 10,000 tons carried through 4 primary load paths. That works out to roughly 2,500 tons each. In other words, each support point on Pad B is carrying nearly double the load. And that's without factoring in the dynamic effects during engine startup. Once you understand that, the design of these pedestals starts to make a lot more sense. First of all, these pedestals are not single monolithic pieces. They are made of 2 separate structural components joined together. The lower portion resembles a typical speed core wall segment, but with some very important differences. At a glance, the outer face plates appear to be similar in thickness and layout to the trench walls. But instead of the standard 10-inch lateral tie bars used in the conventional speed core construction, this section replaces them with 4 massive vertical partition plates, each roughly 3 inches thick. And that distinction is critical. A conventional speed core wall relies on lateral ties because its primary job is to resist bending and contain concrete. The load is distributed across the panel and stabilized horizontally. Meanwhile, the pedestals serve a completely different purpose. They're not stabilizing a wall. Instead, they're carrying concentrated direct vertical compressive loads from the structure above and transferring that load into the wall below. By replacing the lateral ties with thick vertical steel webs, the structure creates a continuous vertical load path. Instead of relying on shear transfer through crossmembers, the compressive forces travel through the vertical steel webs before fanning out into the reinforced wall and ultimately resolving into the pile cap and underlying pile foundation. In effect, this lower section behaves less like a wall and more like a built-up steel column embedded inside of a much larger load distribution system. Sitting on top of that reinforced base is the upper pedestal section, fabricated with 3-inch steel plates on all sides, forming an extremely rigid interface for supporting the launch mount. It's possible that this upper section also contains internal vertical webs similar to the lower assembly, but because the plates are so thick, we don't see any obvious weld seams that would allow us to confirm from these images alone. Just like the pedestals used for the static fire test stand, there's a pattern of gigantic 3-inch bolt holes on the top of the pedestals used to attach the structure once it's in place. Between the 4 legs, there are 80 of these bolts in total. After placing the pedestals onto the wall, they needed to make sure that they didn't have a repeat situation of what happened with the original launch mount back in 2021.
Those are the jacks on each leg.
All right.
The jacks that we got. So on top of that column right there, there's some shim plates. We believe we're off by ½ inch.
½ inch.
Like
Damn,
the
okay.
plane. So what these guys have done, they added plates where we think we're gonna be high, and we'll keep the crane on the whole time while we're jacking. And then Robert, you wanna talk about the lap plates that you guys have?
With how quickly they were moving to get ready for booster testing back then, they were lucky that this didn't turn out to be a bigger issue. Learning from past experiences, before permanently attaching them to the wall below, they placed perfectly straight leveling beams over the top of the pedestals and welded them to the mating surface. I was unable to find it in these images, but I'm assuming there was some kind of laser total station or 3D scanner used to verify the positioning before permanently locking it in. Once they were satisfied, the remaining wall sections were built up around the pedestals. As you can see, the height of the wall is slightly shorter than the top of the mounting surface. This was intentionally designed so that the launch mount would not be resting on the walls. This is why I make the distinction between load-bearing and non-load-bearing wall sections. Zooming in, we can see a relatively large air gap between these non-participating wall sections and the sides of the pedestals. I don't think we have a complete understanding of why this was done, but part of it may have had something to do with allowing them to vibrate and move independently of the wall. As we will see later, another purpose was to provide access for permanently attaching the two structures together. By the time the launch mount was ready to be installed, the wall sections along the two sloped ramps had already been filled with concrete and were awaiting the final touches. After welding the wall sections to either side of the pedestals, these were filled as well and then had the final stainless steel cover plates added over the top. With that, it's time for us to get acquainted with the brand new version 2 launch mount. Alright, we kinda got a little ahead of ourselves there, but I'm doing my best to explain things in a way that reduces the amount of bouncing back and forth between topics. So let's rewind 3 months back to April of 2025. With the flame bucket and ridge cap fully installed, the crew working on the trench walls began preparing for the installation of the launch mount. Checking back on our list of things that need to be solved in order to achieve rapid reusability of the launch pad, the next problem we will address is thermal damage to the external surfaces of the launch ring. This includes pretty much everything above the legs. In the 2-part series, we mentioned the burn panels added to the top of the deck and all over the sides and top of the BQD enclosure. As it turns out, this was super necessary. After 11 flights, the damage to the areas that received direct contact with the exhaust plume during the initial pitch-over maneuver was fairly substantial. Not only are the effects of hot gases melting the steel clearly visible, but when we look closely, you can see that there are holes in the locations where the plugs are welded to the panels after it's attached to the deck. Amazingly, Reagan K on X actually managed to recover one of these plugs out in the wetlands after it flew nearly 200 meters away from the deck. He was nice enough to allow me to borrow it for this episode, which is really awesome because you can actually get an idea of how big these things are. Now, part of the problem here, as I've explained before, is the fact that the stainless steel burn panels used on the deck and booster QD are a different material than the surfaces they are being welded to. This is most obvious when you look at the rusted canopy section, which is clearly a carbon steel alloy. Each of these materials expands and contracts at different rates when exposed to extreme temperatures. This leads to repeated occurrences of cracked welds, which is why crews spent so much time inspecting and repairing them between launches to prevent things like this from happening. In this specific case, the welds didn't necessarily fail, but were more than likely vaporized. As the structure was being demolished, Starship Gazer captured an incredible view of a cross-section cut through the launch mount right next to the booster QD. This is by far the best possible area we can look at when trying to understand the full scope of this problem. If we look closely at the deck, you can see the original 3-inch roof plate, followed by the first 2-inch burn panel that was installed across the entire deck. Surprisingly, there is no air gap between these two layers, contrary to what we initially believed. What we also didn't realize was that the extra panels added to either side of the booster QD were even more substantial than the first layer of burn panels and appear to be approximately 3 inches thick. As we pan from left to right along this cross-section, we're effectively moving backward along the path of the exhaust plume, from regions of later, weaker interaction to the point of first contact. In other words, as the vehicle pitches over, the plume does not engulf the deck uniformly. Instead, it first clips the inner edge of the launch ring at the shortest distance from the engine nozzles. From that initial point of contact, the plume sweeps outward across the deck, producing an almost linear gradient in surface damage from the inner edge towards the outer perimeter. With that said, when we look at the inner edge, we can see that nearly 2/3 of the top layer of steel has been burned away. That's more than 2 inches of steel over a period of 8 launches. Matter of fact, if we look even closer, you can see a gap between the 2 layers of burn panels. This is either a filler plate or molten steel from the oxyacetylene torches that has filled the gap. Either way, I'm fairly certain this gap represents 3 flights worth of erosion before the second panel was added. This explains why the edges of this plug are relatively smooth for the most part. If these were simply cracked welds, the edges would look like this. But where they have been completely vaporized, the edges are smooth. As I've said before, having to constantly inspect and repair hundreds of welds after every launch was one of the biggest limiting factors to allowing for quick turnaround times. Had they gone past Flight 11, the repairs needed to the launch ring would have been a lot more extensive than the 4 previous flights. With that said, the need to constantly add additional shielding and repair welds on the deck and BQD enclosure was simply unsustainable. Luckily, the solution to this is fairly straightforward and kind of a no-brainer. In fact, excluding ULA and Roscosmos, there are not many launch systems out there that do not have some sort of Rainbird system to protect the launch deck. So, why didn't they include something like this from the beginning? Well, from what I can tell, SpaceX did initially have plans of including this type of system when they first began designing the orbital launch mount. This is evidenced by the fact that they had a lot of water piping staged near the launch mount before they even began constructing the integration tower. This type of green painted pipe is almost exclusively used for carrying water. Well, at least at Starbase. Unfortunately, these were never installed, which was most likely a result of environmental regulations. I personally don't believe they were naive enough to think that the world's most powerful rocket wouldn't require some sort of system to cool the external surfaces of the launch deck. Ironically, the first time Elon ever mentioned the need for a water-cooled deck was in response to one of my posts on X 2 weeks before the first integrated flight test. With that said, we fully expected this type of system to be incorporated into the design of Stage 0 2.0. While we didn't know exactly what that would end up looking like, one thing we knew for sure was that they were more than likely not going to use the typical Rainbird system like everyone else in the industry. While Rainbirds are great for cooling the surface of the launch deck after the vehicle has cleared the tower, they wouldn't be very effective during the pad avoidance maneuver. As we've already established, if you have a sheet of water flowing perpendicular to the exhaust plume, the supersonic cutting torch is just going to punch straight through it. This would simply not be enough to prevent it from having its way with the surface of the launch deck. In order for the water to effectively cool the surface during this period, it needs to be ejected directly out of the surface that the exhaust plume is impinging on. This is the only way to maintain a protective layer of water across the surface of the steel deck and shield it from direct contact with the cutting torch. So while the booster bidet system may have not been the best long-term solution for the blast surface, it should prove excellent for the launch deck. But why is it okay for one but not the other? For starters, the launch mount gets spared from any exposure to the plume during static fire tests. That alone reduces the cumulative wear it endures over time. Perhaps more importantly, it doesn't have to deal with the combined thrust of all 33 engines firing from 16 meters away. That 16-meter gap is roughly the same distance between the nozzles and the first shock diamond, which is probably the most destructive part of the plume. The blast surface, on the other hand, experiences sustained exposure to this massive combined shock diamond for a rather long time. In contrast, the deck starts catching a glancing blow from the supersonic exhaust gases once the booster is about 20 meters away. And by the time the center of the plume passes over the deck, it's already climbed another 30 meters or so. As the distance continues to rapidly increase, the damaging effect of the plume diminishes at about the same rate. Overall, the launch deck only experiences a small fraction of the amount of punishment that the blast surface has to endure, which should allow it to last at least 10 times longer, if not more. With that said, let's get into the design and construction of this water-cooled launch deck. In October of 2024, while the jet grouting phase of the flame trench was underway, SpaceX began assembling the first second-generation Starship launch mount. I'm not going to go too deep into the details of its design today. Instead, I'll save that for another episode. What's important to note is that the main superstructure of this launch mount is broken into 3 different layers. The lower level is what I refer to as the fluid stack. As far as its structural purpose, this is similar to the ring skirt attached between the top of the legs on the first launch mount, except it's far larger. In fact, if you took the V1 launch mount, shrank it by 1.5 feet, and then stretched it out into a square, this is exactly what you would get. The fluid stack provides some critical structural support for the launch deck. Without it, I doubt they would be able to get away with only having 4 points of contact in the corners. It would more than likely end up flexing and sagging under its own weight. Conveniently, this massive 8.5-foot tall support structure became the perfect location to mount all of the plumbing for the various gases and liquids that are supplied to the second level. On top of the fluids deck is the mechanical deck, which is just over 50% taller than the original launch ring. As the name implies, this is where all of the mechanical hardware is located. As you can probably guess, above this, forming the roof of the behemoth structure, is the water-cooled launch deck. Similar to the pancake structure for Pad A, the panels that make up this water-cooled jacket are assembled in sections before being mounted and joined together on the roof. There are 8 sections in total, which are each composed of 2 smaller subsections. Each of these sections are prefabricated off-site and have tens of thousands of holes drilled into the 1.5-inch thick plates using a CNC water jet cutter. Considering they are too small to see here, there is a good chance that they are actually just pilot holes, which are later drilled out manually on site. Just like the original pancake, you can see that the partition walls have large, evenly spaced holes to allow cross-flow of water between zones. To keep them from bending and flexing as they're being lifted, an assembly of beams are temporarily welded to the surface of the completed sections. Taking extra precaution to make sure they remain as flat as possible is important considering the plates are resting on top of the inner and outer walls of the deck, as well as the interior partition walls. So the slightest bit of warping can result in large gaps between the 2 joining surfaces. This is also part of the reason why the support beams were left in place during the welding process. Once all 8 slices were lifted and properly adjusted, they could begin the astronomical amount of welding to permanently attach it. This includes both sides of all of the interior and exterior walls. I realize that by continuing to mention all of the welding involved, I'm kind of at risk of this beginning to sound a bit repetitive. But seriously, imagine doing all of this 10 times over. It's ridiculous how much work went into assembling this structure, and I think it's worth acknowledging that effort. On that note, during this process, they realized that they had a bit of a problem on the exterior wall. As you can see, there was about a 1/4 inch gap between the bottom of the plate and the top of the wall. These gaps were much worse in the corners and required a bit of thermal persuasion to flatten them out. Once they were tack welded in the corners, they cut about 2 inches of material off of the top of each wall. This basically left it unsupported along the edge and allowed it to rest fully on the inner partition walls. With those inner walls visible, you can see that the edge of the pancake actually aligns with the end of the partition walls, which leaves an 1.5 inch offset with the outer wall. After shaving down the outer walls, filler plates were added to the back side of the wall, flush with the bottom of the pancake. This eliminated the gap that was originally present, but doubled the amount of welding they had to do in the process. In other words, in a normal situation, they would have welded roof to wall on both sides. Instead, because of the slightly warped roof panel, they shortened the outer wall, placed the filler plates on the back side, and then had to weld wall to filler and then filler to roof on both sides. The point is, this might be an example of how a small tolerance error on a structure of this size can have huge consequences in the form of additional labor to fix the problem. But it's also possible that this is just a sign that they had not finished designing the water distribution manifolds before sending the drawings for the mechanical deck superstructure off for fabrication. Anyway, after welding the interior walls, they moved on to joining the edges of the 8 pancake sections together. As you can see, on each of the upper plates there's a gap between the edges, which allows them to reach in and weld the bottom plates together along the entire length. After this, a filler plate is added between the top plates and then welded on either side. After 12 weeks of non-stop welding, it was finally time to add the first water manifold on the southern-facing side of the launch mount. Sealing off the open side of the pancake is the inlet header manifold, which is made up of 2 long plates, each fitted with 27 evenly spaced inlet pipes, alternating between 6 and 8 inches in diameter. I'm not sure why they didn't just go 7 inches across the board, but it may have something to do with it being an uncommon pipe size. After welding the header in place, they installed a large 24-inch water manifold on the side of the structure. As it was being attached to the mounting brackets, workers began preparing the tops of the pipe studs by cropping them down, alternating between short and tall. This zigzag pattern is likely done to improve welding accessibility in such a dense row of pipes. Once this was complete, they began adding 51 elbow pipes to join the supply to the inlet header manifold over a period of 2 weeks. Now, there should have actually been 54 of these, but mistakes were made. And I don't really feel like going into that explanation, but if you're curious, feel free to pause here and try to identify the problem. While each section of the square-shaped water manifold is unique, this one is most noticeably different, which is due to the fact that it's the only one that will never be directly exposed to the exhaust plume. Instead of requiring its own shielding, it would later be enclosed inside of the shielding for the fluids and controls bunker. As this naked manifold was being installed, another crew began working on the east side manifold. One thing this side shares in common with the other is that it will have a large BQD enclosure on the deck. You can see the footprint of the BQDs outlined on the surface of the plates. The holes within these outlines were either welded shut or were never present to begin with. Even though this section of the water-cooled deck will remain flooded, it doesn't necessarily need to have water actively supplied to it. Because of this, they added a flow-restricting interface plate on the open side of the pancake. As you can see, this reduced the size of the openings for half of the inlets under the BQD, while the others are completely blocked. After this was complete, they could finally install the second water manifold. Instead of using individual pipes, this manifold has a box with partition walls like the pancake, mounted to a 36-inch pipe. After welding it to the outer wall of the table, another filler plate is added to close the gap between the top of the plate and the manifold. It took just over 7 months of non-stop construction to reach this point. Unfortunately, all remaining work would need to take place at the launch site because the GSE crews had a lot of work that could not be completed inside of the fluids bunker until it was installed. On top of that, there were 2 LR11000 super cranes posted up next to the flame trench, anxiously waiting for the big day. So, on May 6th of 2025, just 11 months after breaking ground on the flame trench, the immense 1,200-ton structure was rolled out to the launch site. I hope you can all appreciate how ludicrously capacious this thing is. As I mentioned earlier, the original launch ring was almost exactly 10 feet tall. The version 2 launch mount, on the other hand, is nearly 26 feet tall, which is right around 2.5 stories. With that said, it's no wonder that SpaceX jokingly referred to it as the penthouse apartments. The sheer size of this thing is crazy, and it's amazing how far they deviated from the original plan just a few years earlier.
Like that design, however, everything else we need to take a look at, just like how thick the steel is to begin with. So at least for the next launch mount, we're thinking line boring is the better step. Reduction in mass is going to be huge for us.
Yeah. Yeah, it takes a long time to weld thick steel.
Yeah, they definitely went in the opposite direction on that one, but it's probably for the better. 5 days after arriving to the launch complex, the massive square superstructure was carefully lifted onto the pedestals and secured using 80 gigantic 2.5-inch diameter bolts. This time, they were able to complete the install without relying on hydraulic jacks to level the structure, a clear sign of how much more precise the pedestal preparations were. Over the next 5 weeks, the remaining manifold sections were delivered and installed, completing the square manifold distribution system around the deck. 3 of the 4 corners are joined by large 90-degree elbow sections, creating a clean, continuous loop around the structure. The 4th corner, however, is noticeably different. On the north side, where the primary water inlet is located, there's an odd-looking reducer section before the manifold turns the corner. The pipe necks down from 36 inches to 18 inches before stepping back up into the next section. That's a huge reduction, but you can also see a 14-inch U-shaped bypass partially offsetting the restriction. So what's going on here? When you compare Stage 0 2.0 to the original launch mount, something becomes obvious. On Pad A, the ship's aft flaps clear the edge of the launch mount with plenty of room to spare. But on Pad B, the square geometry of the new deck brings the water manifold extremely close to the ship's flaps during stacking. You might be thinking, why not just shift the lifting position of the vehicle to prevent this from being a problem? Well, unfortunately, that's as far as the chopsticks can reach. So rather than redesign the tower arms, it appears they made a small geometric concession in that one manifold corner to preserve flap clearance during lift operations. As funny as that is, this feature actually does serve another incredibly important purpose. Given the fact that there will be no water being ejected from the launch deck within the footprint of the booster QD, it does make sense to reduce the water flow coming to this side. But between the reducer and the 14-inch bypass, there is still a net reduction of roughly 60% in the amount of water being supplied to the east side manifold, which is far more than you would expect considering the BQD only covers about 25% of the deck on this side. But because this manifold forms a closed loop, restricting flow to the east side doesn't just remove water, it redistributes it elsewhere. That restriction forces a greater share of the total flow towards the north and west manifolds instead. And those just so happen to be the 2 sides that experienced the most direct impingement during the pad avoidance maneuver. So rather than distributing water evenly around the perimeter, the manifold is intentionally biased towards the regions that need it most. What I particularly admire about this is that instead of eliminating the pad avoidance maneuver as many have suggested, they engineered around it by building targeted flow management directly into the plumbing geometry. Overall, this is incredibly well thought out, and the water-cooled launch deck is definitely going to make a monumental contribution towards achieving rapid reusability of Stage 0 2.0. While its primary function is to cool the deck surface, it should also provide secondary protection for the backside of the hold-down arms, the booster QDs, the fluids bunker, the above-grade portion of the trench walls, and even the base of the integration tower. Once the water manifolds were fully welded in place, they began adding the filler plates to close the gap between the manifold outlets and the edge of the pancake. After this, the lower portion of the enclosure for the methane and liquid oxygen BQDs were installed, followed shortly after by the 2 massively upgraded BQDs themselves. Now, there's a ton that I want to say about these new booster QDs, but for now, we'll save that for another episode. The one thing that we should mention that's actually relevant to creating a rapidly reusable structure is that positioning of these QDs was not just a matter of convenience. While it's true that the LOX QD really has nowhere else to go, the methane QD could really be positioned on either side of the LOX. Locating it opposite of the integration tower was important for keeping it from becoming the center of attention for Super Heavy's exhaust plume during the pad avoidance maneuver. By eliminating direct impingement on the enclosures, the critical components that they are protecting are far less likely to experience the type of damage sustained to the version 1 QD over the first 11 test flights. Compared to that, these will definitely be living the good life. Along with that, by separating the methane and oxygen into 2 separate QDs, it completely eliminates the risk of forming a combustible mixture inside of a shared enclosure. Even small leaks during disconnect operations can create hazardous conditions if fuel and oxidizer are allowed to accumulate in the same confined space. Keeping those systems physically isolated adds an additional layer of passive safety. And this crosses 3 more items off of our list from Part 1. After the QDs came the forward section of the 2 enclosures, followed by the upgraded blast doors. Meanwhile, the crew responsible for the trench wall construction began adding the final sloped sections up to the deck, which integrate seamlessly with the square water manifolds. Along with this, the GSE crews had finished installing all of the major components of the fluids bunker, which allowed them to begin adding the extremely heavy-duty protective cladding around the structure. While we haven't really discussed it much in this episode, this massive GSE bunker is another major departure from the original launch mount design. On version 1, much of the electrical hardware, pneumatic systems, and insulated cryogenic plumbing were mounted directly to the exterior of the structure, fully exposed to both convective and radiant heat, reflected overpressure, and hot gas intrusion. Now, all of those critical systems are consolidated inside of a reinforced bunker, physically isolated from the plume environment. Instead of trying to shield hundreds of individual components, they've simply removed them from the battlefield entirely. Inside the trench, the final steps of enforcing the restraining order were underway. In Part 1, we discussed the stainless steel panels installed along the floor of the trench. That was actually way out of order, but it made sense to cover that as we were talking about the pile cap embeds. In reality, that process didn't start until well after the launch mount was installed. Before reaching the final steps of that installation process, they had to complete the transition from the sloped ramp to the grade level slab surrounding the trench. On the eastern side, a pattern of CFA piles was installed before forming the concrete slab tying the ramp into the surrounding driveway. These CFA piles are likely intended to keep the concrete from being lifted by the pressure differential created by the exhaust plume as it separates from the surface of the ramp at an angle. The last thing you want is to be throwing concrete hundreds of meters away into the former wetlands. Once this concrete was in place, they installed curved panels along the ends of the ramp, creating a smooth transition to the concrete driveway. On the west side, the commodities trench was already constructed on top of an arrangement of CFA piles, so all they had to do was tie the exits of the ramp into the slab covering the underground culvert. As both sides were being completed, they also began to address the exposed bolts for the flanges along the base of the speed core walls. To cover these, curved plates were installed along the entire length of the walls, leading up out of the trench. Not only does this protect the bolts, but it also eliminates the sharp corner between the floor and the walls, which reduces localized erosion. The feeling I had the first time I saw these took me back to the day when I first noticed the painted flame diverters on the OG launch mount. For some reason, this is one of my favorite features. Something tells me I won't end up being disillusioned this time, though. By the end of November, the exposed water manifold on the south side of the launch deck was enclosed in shielding from the top of the bunker. Long rectangular panels were added over the gap between the bunker and the trench walls to protect the 2 opposing stairways. Large, downward-facing steel ducts were installed over all of the external vents, and 2 gigantic bank vault-style doors were added to the 2 main entryways, separating the lock side of the bunker from the fuel side, while smaller bulkhead doors were installed leading into the 2 stairways. Once the flexible GSE plumbing was finished being connected to the BQDs, the midsection of the 2 enclosures were installed, followed shortly after by the retractable doors for the hold-down arms. And finally, as I was recording this, we realized that at the bottom of the flame deflector, they began adding vertical mounting tabs in the small gap between the ends of the pipes and the foot of the step. After adding panels over the top, the space between the pipes is almost completely sealed off, which nearly eliminates all possibility of hot gases circulating beneath the structure. The only open access to the underside of the structure is the opening on either side of the ramp. I have a feeling there will also be an enclosure sealing this off once they're sure they will never need to access this area again. Now that we can see the completed structure in its entirety, we can step back and make an important observation. When we compare Stage 0 2.0 to the original launch mount, what's the first thing you notice? For some of you, it might be that it looks like a comically oversized Cybertruck. And while that's certainly true, let's evaluate it not as a shape, but as a system. What I'm actually referring to is something far more deliberate: the overall choice and placement of material across the structure. I know there's been a fair amount of repetition throughout this episode, especially when it comes to welding and identifying different types of steel. But that repetition has been intentional. Because once you look at the structure as a whole, it becomes clear that there has been a massive evolution in engineering priorities. Where material selection and weld strategy previously appeared to be more of an afterthought, for Stage 0 2.0, those concepts were central to the design philosophy. So with that in mind, let's quickly take inventory of the different types of steel used throughout the structure. Starting with the speed core walls, while they may appear to be entirely stainless steel, that's actually not the case. When we examine two wall panels side by side, the trench-facing surface appears to be stainless, while the outward-facing surface is harder to identify due to the external coating. A label on one of the panels confirms that the trench-facing plate is 304L stainless steel, while the internal tie bars, which are embedded in concrete, are ASTM A500. I should note that while I am a mechanical engineer, I'm definitely not a material scientist. With that said, I think the rust visible along some of the exposed edges strongly suggests that the outward-facing plates are a carbon steel alloy, likely something in the ASTM A36 or A572 family. The surface coating differs depending on whether the section is below or above grade. Below grade sections, like those mounted on the floor of the trench, are coated in a glossy black finish that is likely an asphalt-based coating. This type of coating is well suited for blocking water ingress and improving resistance to alkaline exposure from concrete. In contrast, above-grade sections are finished with a zinc-rich primer, which is a much better choice for open-air exposure where ultraviolet radiation, humidity, and salt spray are constant threats. The superstructure of the launch mount appears to be made from a similar carbon steel alloy with the same zinc-rich primer, while the water-cooled deck is stainless steel. It's important to note that after the water manifolds are added, none of the welds between these two materials will remain exposed. The launch mount is welded to the outer-facing carbon steel trench walls on one side, and on the opposite side is welded to the stainless steel interior walls. The lower enclosures for the BQDs are both made of carbon steel. The primary attachment for the LOX enclosure is a carbon-to-carbon weld with the frame of the bunker. Once the cladding for the bunker is added, there's a mixed species weld around the perimeter. The bunker shielding panels are also welded to the carbon steel frame, but the gap between panels is later covered with a stainless steel strip, effectively shielding the weld between the two dissimilar materials. The vent covers appear to be galvanized steel welded to the stainless bunker cladding. The methane QD enclosure has the same species weld with the side of the launch mount, followed by a carbon to stainless weld around the water manifold, the trench wall, and a stainless steel cover plate on the other side. The midsections of the enclosure are also carbon steel, but these are bolted on instead of welded to allow them to be removable, so we can just ignore those. Finally, we have the front section of the enclosures, which are clearly stainless, attached to the stainless steel deck. I'm not sure why they didn't just go stainless across the board with these enclosures, and even the vent covers, but that's besides the point. When we take a step back and look at the locations where these mixed species carbon to stainless steel welds are occurring, it paints a very interesting picture. Now let's compare this with the original launch mount. Nearly every exposed weld between dissimilar metals is located in an area that experiences little to no direct impingement from the exhaust plume. The one notable exception to this is in the flame trench, where nearly every exposed surface is stainless steel, except for the bottom of the launch deck. Here we find the only carbon to stainless steel weld that exists in what I would consider to be a potentially harsh thermal environment. While it will be extremely hot in the trench, these joints are largely out of the direct plume path. Even so, considerable effort was put into protecting what may be the most critical weld on the entire structure. The obvious place to look for a carbon to stainless weld would be where the launch mount meets the pedestal. But as it turns out, the real transition between materials isn't where most people would expect it. It's actually about 3 inches lower. Yeah, huge difference, right? Just like the rear-facing plate, the 3-inch thick mounting surface that the launch mount is bolted and later welded to is actually made of carbon steel. The front-facing plates are clearly stainless. The side plates, however, were coated prior to installation, which, based on everything else we've covered, might suggest carbon steel. But given the incredibly deliberate material zoning throughout the trench and the thermal environment these pedestals are designed to endure, it would be extremely surprising if those partially exposed surfaces were made of carbon steel. So, assuming that's the case, the only weld that actually matters, or more accurately, the only one that truly needs protection, is the joint between the carbon steel mounting plate and the stainless steel outer shell of the pedestal. This interface sits directly beneath the launch mount and exists within an environment that will experience extreme thermal fluctuations even if it's not in the direct path of the plume. So let's take a look at what they did to protect it. This is where those intentional air gaps around the pedestals and between the bottom of the launch deck and the top of the load-bearing wall section finally come back into play. Without those gaps, crews would not have been able to complete a full perimeter weld around the pedestal interfaces. The side gaps also allowed them to install ceramic heating pads to maintain proper preheat temperatures during welding. You may have noticed these being used all over the launch mount as it was constructed. Preheating is critical when welding thick carbon steel sections. It reduces thermal shock, slows cooling rates, and helps prevent hydrogen-induced cracking in the heat-affected zone. That level of thermal control is something that I don't believe we ever observed during fabrication of the original launch mount. After completing the primary welds, the joints were ground smooth before thick steel cover plates were installed, forming a collar that wraps around 3 sides of the pedestal. These plates conceal both the structural weld and the carbon to stainless transition zone between them. On top of that, an even thicker layer of plates was added to the 2 inward-facing sides. These surfaces have the highest exposure to reflected radiant heat from inside the trench. After this, yet another horizontal plate was added to cover the seam between the first and second layer of shielding. Long square bars were then installed over the remaining gaps on either side of the pedestals to prevent superheated moist gases from flowing through the space between the legs. I think we can all agree that nobody wants that. And just in case all of this wasn't enough, 1.5-inch thick stainless steel burn panels were installed over every exposed weld, tying the pedestals into the surrounding wall. When you compare the before and after, it becomes clear that the Stage Zero team was definitely not f***ing around. This wasn't about strength. It was about creating a massive thermal barrier that eliminates every possible pathway for heat and gas to reach the most critical welds in the entire structure. Now, at first glance, everything we've just covered might suggest that SpaceX learned a very hard lesson constructing the original launch mount out of what looked like a metallurgical buffet of dissimilar steel alloys. But it's also worth considering the possibility that this wasn't accidental at all. As I explained in part 1, the original launch mount was, in many ways, a full-scale experiment, and using different alloys in different locations may have been an intentional way to gather real-world data on how each material performed under extreme thermal and mechanical loads. Whether that's true or not, I'd say they definitely knocked it out of the park with this complete overhaul of their launch infrastructure. While my opinion doesn't necessarily matter in the grand scheme of things, I feel pretty confident in saying that this will vastly exceed the durability of the original launch mount, and I'm really excited to finally see it in action. In part 3, we will go even deeper into the flame deflector and water-cooled launch deck by examining the inner workings of the water distribution system. I promise you won't want to miss that one because I'm sure many of you have been waiting for a long time to learn about these baby Raptors being used to pressurize the water tanks. Sometime in the next few days, I'll be releasing an early access QC version of that episode, which will be available to Patreon supporters and members of the channel as soon as it's ready. On that note, if you would like to support what we do here, Patreon is by far the best way. Before we wrap things up, I have one last thing for those of you who actually watched the 2-part Stage Zero Rapid Reusability issue series back when it was released. I have a feeling that at least a handful of you have already left a comment on this video before reaching this point. And those comments probably say something along the lines of, "Wow," all caps. So are you really just going to pretend like the obsessive speculation about an interchangeable launch mount never happened? Well, I'm sure by now that most of you know I have no problem admitting when I'm wrong, and in reality, it's actually part of the fun. I have to admit that I can't even look at the launch mount pedestals without thinking about this. Those of you who follow CSI Starbase on X will probably know that the method of mounting the launch mount onto the trench wall was something I was anticipating long in advance. Using bolts to secure the structure in place was, ironically, the main thing holding together my theory that SpaceX was intending for this to be an interchangeable launch structure. In fact, I was 90% convinced that this was the case up until the moment where they began welding the launch mount to the pedestals. Had this episode been released in the order I originally planned, I would have included this long, detailed explanation of everything that would have been required in order to enable the structure to be temporarily removed or fully replaced in less than 2 weeks. Obviously, that is now completely irrelevant, but I do think it's worth briefly explaining why I believed an interchangeable launch mount was necessary. If I'm being honest, I have to admit I was not expecting the final product to be anywhere near as impressive as it is. This is literally the first time I've looked at a piece of infrastructure at Starbase and thought, damn, that shit is literally perfect. If I could leave a Yelp review for the team that designed this, it would say 5 stars, no suggestion for improvement. That said, if you were to ask me if I think it's physically possible to create a structure that can continually withstand this type of abuse for years without eventually requiring some type of major refurbishment, my answer would still be no. Although I would love to be proven wrong. Put simply, Super Heavy is an absolute monster, one that hasn't even reached its final form yet. This is without a doubt one of the most extreme man-made environments that exists anywhere on Earth. It might take 50 to 100 launches, But just like the booster bidet system on Pad A, eventually one or more critical components will reach the point where they are no longer safe to use. If I was a betting man, I would put my money on either the ridge cap or both of the flame buckets requiring repairs before anything else. A potential example of this occurred on January 15th of this year at SpaceX's McGregor facility. 3 days after a particularly spicy static fire that sent black smoke billowing out of the trench, the flame bucket was apparently removed. Unfortunately, without knowing exactly what happened, we can only speculate. But one thing is for sure, when you look at NSF's flyover images taken less than 2 weeks before this occurred, it did not appear to be in the best of conditions. Given that it logged an impressive 114,866 seconds of hot fire testing since 2022, I would not be surprised if this was a structural fatigue failure of the flame bucket. If that's the case, I have a feeling that they more than likely expected this to happen and that this may have actually been an intentional test of failure. There are so many random experimental tests happening at McGregor that I would actually be more surprised to find out that they weren't using this data as some kind of benchmark to estimate the service life of Pad B's deflector system. While it's possible to repair these flame buckets in place, as we've seen with the flame trench at Massey's, it might be faster to just replace them outright. This, of course, assumes you weren't caught off guard and had another one ready to go. Another assumption I made early in the construction process was that there would be some sort of partial roof structure over the trench to support a retractable service platform. That would have made an eventual flame bucket replacement far more difficult without moving the launch deck. Since SpaceX ultimately chose not to include that feature, a full replacement is likely more feasible than I originally expected, though still requiring a bit of finesse. With that said, my view on whether an interchangeable launch mount is truly necessary has definitely softened, though it has not changed completely. The good news is that SpaceX is in various stages of completion on 5 different launch pads, and if I had to guess, they will all come online within 6 to 9 months of each other. Hopefully this staggered commissioning sequence will result in them never having more than one pad down for heavy maintenance at a time. Anyway, hopefully that brief explanation satisfies those of you who wanted me to explain my thinking.